Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 25, and we're in chapter 8, starting to talk about multiple regression. Last time we talked about the ANOVA table and the fundamental equation of regression analysis, and we looked at the hypothesis test for the significance of the model, whether the model is significant. And as we move into a multiple regression, that test is very important. We can still test for the slope, but we're going to have more than one variable, and so testing for any one of those individually doesn't test the whole model. And so we'll see some difference. So in this chapter, we're looking at multiple regression models. We're going to take a look at the problem graphically as well as we can, talk about some assumptions, how we get the best equation, the ANOVA table, the expanded ANOVA table, and some examples. So this is an extension of straight line regression where we have more than one independent variable. And so it says we can establish matrix notations. We're not going to really get into the matrix too much in this course. If we do establish the matrix algebra for a straight line regression, it's easy enough to extend that to the multiple regression as far as parameter estimates and inferences. So there are some difficulties in dealing with multiple regression. The first is the one that we deal with a lot, which is the best model. Also, it's difficult to visualize because if we have more than two independent variables, we end up with more than 3 dimensions, and we can't draw that. It's also difficult to interpret the model in real-life terms sometimes. And of course, there's an increased computational complexities, but that is not as much of an issue these days with better computers, except that we've gotten into bigger data. And so then again, the bigger the data set, the slower it runs. Okay, so what is a multiple regression model? It can be considered, there's several ways to look at a multiple regression. It could be that we're going to take one variable and also look at its square. So if we have something that looks like a parabola, or it could look like a parabola in that direction, then we may want to consider the square, and we may have also a term that's not squared of the same variable in this case. So, but many times this is how we represent it. Let's take a look. So what we do is we have the intercept, and then the first variable is x1, and the second variable is x2, and we say beta 1 and beta 2. And x1 can really be anything. It could be x1 squared, it could be x1 to the fourth, it could be any power of something. We really just notate it as x2 in most cases. All right, so that can be sometimes confusing, but as it says here, we can let x1 equals x and x2 equals x squared. So this is the general form, and that's usually what you'll see, but not always. So so another example can come from cases when we have more than one basic independent variables. As I just mentioned, x2 could be something that's not related to x1 at all. And we do that as well. So here we're going to study the weight and height and age for children that have a nutritional deficiency. So weight is going to be our dependent variable, and the two independents are going to be height and age. Okay? So you say, well, is height and age really independent? It can be, yes, because not everybody grows to the same height, and after a certain age or within, as long as you're keeping them within, well, no, different ages, you're going to see a relationship, but we're going to consider height and age independent. Okay, and so here's our data. We have we have 12 children. Here we have our weight, we have our height, and we have our age. So we've assigned y, x1, x2. And so if we're interested in first order terms, we may look at this equation. If we want to consider an additional term, let's say x1 squared, we'll probably call it x3. And then our equation looks like this. Notice that we always have our error, because that's a statistical model. If we have error, without it, it's a deterministic model, and that's not what we're talking about in this class. And again, if we want to consider all the possible second order terms, that means if we have x1 and x2, that means we need x1 squared and x2 squared. And then we could have also x1 times x2. So here we've let x3 be x1 squared, x2 squared is x4, and x1, x2 is x5. So we don't consider choosing the best model in this chapter. We'll wait till chapter 16 to do that and do it formally. Okay, so let's look at the problem graphically. If we only have one independent variable, then we've seen that. Here we have maybe a parabolic or second order relationship. And so it's easy to graph in 2 dimensions. If we go over to more than 2 dimensions, we get into 3 dimensions, we think of something as a plane in the not xyz, but x1, or x1, x2, y in this case. All right, and so we can think of that as a plane in 3-dimensional space. And we really think of it as a hypersurface if it's in k plus 1 dimensional space. Again, for k equals 2, we have a surface in 3-dimensional space. And we're trying to fit this hyperplane or hypersurface to the scatter points, and we're trying to make the best fit. So it says, just as the simplest curve in 2-dimensional space is a straight line, the simplest in 3-dimensional space is a plane. That's not place. Plane, which has the form y equals beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Don't forget the epsilon. Okay. And we can find the best fitting plane using least squares method, the same thing that we used for the straight line regression. And so if you look, we let q equal the sum of squares of y minus yi hat, and then we substitute in for yi hat. We have this lovely equation, and then we can take derivatives with respect to x1, we can take derivatives with respect to x2, and we can solve these equations and come up with the ideal best fit equation for the line or for the plane through the points. Okay, so that's what this looks like, just an introduction of what we're doing. We're adding more variables, and things are going to get more complicated. I think you can see that. But luckily, we have a computer. We don't have to do this by hand like we did 30 years ago when I did this. All the calculations were by hand, so that was really fun. Actually, I did enjoy it. But now we can do so much more because we have the computers that's already programmed to do it. Okay, so I hope you're starting to get a little excited about the topic, because it's really starting to get interesting now, and what we can do to try to figure out the relationships, the associations between these different variables, and I just still think it's really cool. So I hope you are getting interested in this. So don't forget to scan your lecture notes by midnight, the date listed on the course calendar. Update your formula sheet. You might need something from what we just did. You might want to make some notes of things to make sure that you have the notation right. If you have questions, please come to virtual office hours. If you can't make it to office hours and you have an urgent question or you need some help, by all means, email me, send me a picture of the problem, because I may not be able to get to the problem right then, and send me a picture of your work. That way, together, I can help you pretty quickly through email, or we may be able to set up a time if it works for both of us to meet. All right. Well, you take care, and I will see you next time.